Okay, so
sorry,
you already said something, but it's okay. So
Okay.
okay, so I'm just gonna respond.
Should I start or should I wait for an introduction?
Load your document. Done. Perfect.
Should I wait for an introduction or should I just start? Or?
Let me just.
Okay.
Let's start.
Can you start? Hi, I am François-René Rideau from Mutual Knowledge Systems, and I'm going to tell you about simple verified DApps, and not just for smart contracts, and why DApps are the very hardest programs to write, and why, well, something is cut. Okay, introduction, the hardest programs to write. DApps are a billion-dollar market, $7 billion in 2018, 17 now, and it's headed toward trillions if we take over finance, but right now, instead of having a nice S-curve, it's slumping. Why? Well, there are circumstantial reasons, but also structural reasons. We have a vicious cycle of no good tech, no good apps, no good users, no money, etc. And of course, every vicious circle is a virtuous circle. If only we had more good tech, we could have more good apps and more users and more money, etc. So it's a bootstrapping issue, and the question is, what tech should we work on next since we are techies? There is scalability. I think there are people who do great scalability here. Portability, no one does great portability. Interoperability neither, usability neither. But the main thing that makes DApps so hard to write and so damn expensive and impossible to use now is security. We don't know how to write DApps that are secure, which means that it's extremely costly, risky, and volatile to use DApps. Costly. The smallest, simplest DApp will cost you about $80,000 to write, but mostly to audit. Maybe only $20,000 to write, and then a whole chunk of money to audit it. And it will still be unsafe. The best apps written by the best experts with the best track record, only 400 lines, have lost hundreds of millions of dollars again and again. And so if you have $1 million DApp, no amount of auditing can prove it correct, so you will only run it on permissioned blockchains, which means, not real blockchain. And volatility, of course, at the end of all your efforts, your DApp will only run on one blockchain, say Ethereum, maybe the best, maybe not. We hope it will be the best. We're trying to make it the best, but maybe not, which means that there is volatility associated to using a single chain, and volatility associated to having to choose your chain. But what if we could solve these issues? What if we could slash the development cost by 90% or more? What if we could make the risks so much less that normal programmers can write a DApp that is today infeasible? What if DApps could run on any blockchain? You write it once, it runs anywhere. That's what I'm trying to do with mutual knowledge systems. So let's go back to why blockchain security is so hard. It's so hard for these 5 reasons. There is zero tolerance to bug. If you have one bug, it can be 400 lines of code, 1 million lines of code, one bug, you lose all your money, all your customers lose all your money, and there is no recourse. The whole point of a public blockchain is there's no one to make you wrong, and there's no one to make you right. Bug, you're dead. All code is fragile. That's not specific to DApps, but most code is written with languages and methodologies that assume it's OK to make mistakes. Just fix the bug, release the software again. That's fine. But for DApps, that's not OK. If you have a bug in your DApp, you have lost all your money. Boom. With DApps, we have active adversaries. It's not just like most applications where if the bug only happens by a full moon and it's raining, well, odds are it doesn't matter much and at midnight. But if a DApp has a bug that only happens at midnight when it's raining by a full moon, well, guess what? There is someone in Ukraine who will contrive to call your DApp just on a full moon at midnight while it's raining and steal all your money. You have active adversaries. The only other guys who have active adversaries are the military or the secret services. But they keep their code secret behind armored guards and private networks. DApps run on the public networks where anyone can interact with it, and all the code is public, and it has to be because you have to convince the other parties who will be your enemies that the code is correct. So you have to show them the code so they can look at the code and analyze it and break it. And finally, all the known techniques used to reason about programs are insufficient for DApps. when you go to university and you learn how to prove a program correct and reason about a program, you assume that all parts of the programs conspire to the same result, that everyone cooperates. And this is exactly the thing you cannot assume with a DApp. The whole reason you have a smart contract is because you do not trust the other party to cooperate. The goal of the smart contract is to create the incentives for the other party to cooperate. Therefore, you must have the cooperation as an output of your contract as an input to it. You must prove that your contract aligns the incentives. You can assume that your contract aligns the incentives and the people will cooperate. So for all these reasons, DApps are the single hardest programs for anyone to write. If you think writing a DApp is easy, you're fooling yourself. And none of the existing techniques will help you write DApps. Of course, you want to use logic. Dijkstra is famous for saying that all code must be proven correct before it's run. And maybe he was wrong for code in general. He was proven wrong for code in general. But I think he was right for DApps. You don't want to write the DApp and run it before you know for sure that it's correct. Maybe you want a toy DApp and run it for $5 before it's correct. You don't want to put $1 million or $1 billion in a DApp that has not been proven correct. DApps require domain-specific logic. You need more than the usual logical tools. And you can't do the logic afterward. You can't first write your DApp in Solidity and then hope to prove it correct. That's low probability of working, especially if your DApp is big. To write the DApp correct, you must use a language or a system that is designed for proving the DApp correct. And as you write the DApp, make sure that at each step you do everything designed to make it correct, because you can't do that after the fact. If you didn't do that beforehand, the best way to prove your DApp correct is to scratch it and start again using the correct method. And of course, complexity makes logic intractable. If you have a very complex program, you will never be able to find the proof automatically, and most users won't be able to find it by hand, so it will be impossible to prove it correct. To prove the program correct, you must keep it absolutely simple, and simple in terms of mathematics, not necessarily simple in terms of human discussion. So you want to keep your DApp in a way that is very simple. And then you can use automation and automatically prove your things correct. And of course you say, oh, it's too complex, it's too expensive. Why should I bother with automating logic? Well, if you think that it's costly to use logic, you haven't yet built a $1 billion app that does not use logic and that loses all its money because the bad guys will use logic. They will either hire or enslave a mathematician from China or Russia, and he will break your app, he will use the tools. So, hi, our Ukrainian friends. So that's where mutual knowledge system is trying to solve these problems. We have a domain-specific language, a DApp, a DSL for DApps. It uses domain-specific logic designed just for DApps. And when I say DApps, I mean not just a smart contract, but also the matching client and server code. Because if your DApp is perfectly correct, but you have a bug in your client or server code, someone is going to lose all their money. Maybe not everyone is going to lose all their money, but someone is going to lose all their money too. So that's something you don't want. So we are a Moon. We're looking for early customers and investors, but I'll come back to that later. First, let's present our language, Glow, which is our DApp language. So what's a DApp first? A DApp is an interaction. People will exchange messages. Who are these people? There are multiple people who don't trust each other, or have maybe a limited trust, but basically no trust between each other. And as part of these interactions, they will exchange assets on public ledgers. And these assets will be subject to rules that they can verify. So you can have a computer check that everyone did or did not do their thing. Hello. Oh, sorry. And so here's a simple program that illustrates essential things about interactions. It's only 22 lines of code, and it illustrates the main problems. It's a rock, paper, scissors. So rock, paper, scissors is a simple game where two people choose at the same time a hand, rock, paper, or scissors, and rock beats scissors, that beats paper, that beats rock. That's easy. except that on the blockchain, there is no such thing as at the same time. So let's first look at the set. Oh, no. Oh, no, it's cut. That will make things more complex. OK, so doesn't display correctly at this resolution. So you have a data. OK, you have a data type hand that's rock, paper, or scissors, an outcome, and you compute the winner through this kind of magic formula that I don't want to. That's on 7 lines. When you zoom on the interaction, that's not going to. Can we use a. Sorry, let me try to use my computer because this is not working very well. Is there. Do you have HDMI? Do you have HDMI cable?
Try to unzoom on this first.
Okay. I would like to show the source code on one.
Try to dezoom on here.
Well, otherwise I can talk about it. Okay, let's talk about it then. Can you control minus or something? Control alt minus or? No. Okay. No. Well. Okay. So in this program.
1 second.
Oh, and okay, and you can zoom. Oh, you have a scroll bar. That's better than nothing, I suppose. That's not good.
Aha.
Aha, more. Plus, 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 plus. Again. Ooh, good. Thanks. Okay. So when you zoom on the, I put some colors. You have some things are done by Alice, A. Some things are done by Bob, and some things are done by Alice. The way it works is that we can't publish messages at the same time, so Alice will first choose a hand and commit to this hand by publishing a digest of this hand and some salt, some random salt that she chooses. This way, Bob knows that Alice cannot change her mind and choose the hand that will beat him after the fact. Alice has to commit to a hand first, and then Bob will reveal his hand, and then Alice will reveal her hand and the salt, and we can check that the commitment is correct. So when we verify the commitment, we verify the formula that's above. And whenever Alice defines her hand or her salt, only she can see it until it's published, which will be much later. When she publishes her commitment and computes her commitment and publishes it, then Bob can see it. But otherwise, variables remain private, which means that we have a specification where when we have the godly view, God can see both what Alice and Bob has. We can reason about what's going to happen. But when we will compile this program to Alice's client and Bob's client, Alice will only be able to see her variable and what has been published by Bob. Bob will only be able to see his variable and what has been published by Alice, and everyone will be safe. And so the rest is less interesting. Oh, yes, input hand. We are going to have a UI, but the UI will be separated from the program and isolated for the blockchain. So the UI will be written in a different language. This is a language Glow that looks a bit like JavaScript or TypeScript or ReasonML. But your interface will be written in a separate module that will be isolated from the blockchain. So you will not be able to talk directly to the blockchain. You will talk only to this module or that is safe. OK. So the smart contract generated is about 3 times the size of my program. No time to look at it. The client is also about the same size, but that's a generated client. If you need to write it by hand, it will be much harder and longer. I wrote my first version by hand just to see how much it would be, like 5 times longer than that, or 3, 4 times. Same thing, the client for the other player, Bob. And we also generate interface declarations, of course. We generate a logic spec. Unhappily, it's not readable. It's part of my to-do list to make the spec readable. But what the kind of things we prove is first that the ledger is always balanced, that when everyone cooperates, the liveness properties hold, whatever the liveness properties are. So there are some that are built into the system and some you want to define yourself. The safety property is a thing that no one on the market even thinks about. It's the fact that you want to prove that even if the other party does not cooperate, the interaction is fine for you. You will not, if Alice times out, Bob can say, hey, Alice timed out. She loses, and she forfeited her wager amount. Similarly, if Bob times out, Alice can say, hey, Bob timed out, I can get back my money. There is no money that will get locked up. There will be no other bad things that will happen to Alice or Bob if the other fails to cooperate. And of course, a lot of the specs will have to be user-specified, such as the two assertions I added in my program that said it was safe for Alice and Bob to play. I cannot guess that as an author of the programming language. You will have to write those things. The programming language can make it much simpler for you to write and even express those things that are not at all expressible in other programming languages, but you still have to write the properties you need to prove for your app. That's app-specific. The one can do that for you. It's not magic. So what else do we automate? We automate adding, for example, an escrow. What if Alice chooses paper and Bob chooses scissors? And then Alice, oh, I'm going to lose. Why should I cooperate and publish the last message? She shouldn't. And then Bob will time out and the loser wastes a lot of time. But if Alice has to deposit a sufficiently high escrow that can be automatically added and computed, then she's incentivized to keep cooperating even if she loses. Okay, she lost, but if she does not cooperate, she will lose the wager amount and the escrow amount. So she still cooperates and shows her hand. And in any interaction where you have a future message, you need to deposit an escrow beforehand. We can also Merkleize the contract state. We didn't see that, but it's an optimization that will save you a lot of gas. And you really don't want to write this optimization by hand when you write in Solidity, because you will get it wrong, or you will modify your program later, and that will make it wrong. And then the type-CC will not help you. So Merkleization of state will save you a lot of gas, and it can be done automatically for you by our language. We can use also generalized state channels. If you use a generalized state channel today, you must make sure that your JavaScript program and your Solidity program or your Go program, whatever you use, are perfectly in sync, even as you modify your program. That's extremely hard. We can generate everything from the same spec. In the future, we can also use MAST and zk-snarks to add privacy to our contracts so that no one else but the contractors know what's in the contract. And of course, in the future, we can also generate code for any blockchain. There's nothing Ethereum-specific in my programming language. Why does it matter? Well, we have better DApps for a fraction of the cost, literally 10 times fewer code than if you had to write it by hand. The code stays automatically in sync when the spec evolves. That's very important because the spec will evolve. That's bit rot. It's safer because you can actually express, using logic, the things that matter to your app. You're not proving a model of your app. You're proving the implementation of your app. You can do optimizations you wouldn't afford by hand, such as Merkleization of state. And it will be portable to any blockchain. So we're solving a lot of hard problems for app developers. We're the right company because this requires skills in blockchain, but also in economics, in computing, in logic, and in design. And if you miss one of them, you will not even know that you are missing it, and you will do things wrong. I've done this kind of things all my career long at IT Software, Google, and Bridgewater, where I built software to make it simpler and safer for individuals and large teams to write code. And I left research for industry precisely because I wanted to build systems. But I still kept a lot of contacts in research. That's why I have a lot of people I know who can help me build a good language. How much time do I have to discuss attack models? A bit of time. Let's discuss attack models. That's very important. So a lot of major failures in the past can be attributed to what I would call abstraction failures. The DAO hack is a reentrancy issue. Why do you even have reentrancy problems in the EVM? Maybe you have them in the EVM, but you should certainly not expose that to the language you use to program applications. In my language, there is no reentrancy issue because there's no possible reentrancy with any state that can be used twice. So no reentrancy issue, no DAO hack possible. Priority wallet hack, bad access delegation. the notion of delegate code and delegating to a contract should not be visible to the language. It's an implementation details. You still need to get it right, but you can get it right once for all your applications, and you don't have to get it right or wrong for your language. Priority OLED hack number 2, it's a library destruction. That's again, it's an abstraction failure. Many other hacks are bad or missing permission checks. This is also an abstraction failure. In my language, everything is done by some participant. And your safety theorem says that you are safe whatever the other participant does. So if something allows anyone to destroy the code or to steal your money, you will be incapable of proving the safety property because it will be trivial to show, no, you're not safe because, hey, this guy can take your money. So you will not be able to prove the safety property. Therefore, you will detect early on that, hey, I should not run this app. The safety property is not there. So abstraction failures. And the solution is to have a better programming model. And yes, you still need to implement it well. But the implementation effort can be shared between all apps instead of every DApp developer having to get it right and then learn all the tricks of the EVM. Misplaced trust. I cannot solve that. If you trust the bad exchange and give them your money and they run away with it, or if you trust the bad oracle and someone's oracle starts lying and your money is worth nothing, I cannot help you with that directly, but I can do two things. I can make the trust assumptions explicit so that when you try to run the app says, beware, if you run this app, you are going to trust this operator as custodial of your money, or this operator as your oracle. So do you choose to trust this oracle? You can still choose to trust it, but you know that it's centralized and you know whom to blame if things go wrong. And of course, as killer dApps, maybe we can build the non-custodial DEX or decentralized oracles, and I believe it will be much easier to write these things in a portable way and safer way using my language than without. Okay, low-level attacks. How much time? Sure. One low-level attack, okay, you can have network DDoS. So I know where your computer is. I will just DDoS it, so you cannot post your transaction on time, and therefore you will time out, and I will collect your money. So if you are going to play poker or any high-stake contract on Ethereum, you have to make sure that you will be able to post the final transaction before the deadline. Otherwise, you lose all your money. And if it's a $10 thing, I won't do anything against you. But if it's $1 million transaction, I will cut your internet line. I will destroy your satellite connection. I will do lots of bad things for you to get to $1 million or $10 million or $1 billion and prevent you from posting the transactions that would make you have it. I can also do a FOMO 3D attack. Oh, that's one of my favorite. Who here has heard of FOMO 3D? Okay. If you haven't, you should read. It's beautiful. Basically, these guys prevented his rivals from posting their final transaction, their next transaction, and making them time out by buying the entire Ethereum blockchain for 5 minutes. And so for some like tens of thousands of dollars, he collected $1 million prize the right way. So if you don't have an economist at work in your team, you will not be able to survive this kind of attack. Who here has a DApp and does not have an economist to do that right? Okay, well, you better either hire one or hire the services of someone who hires one, because otherwise your DApp will fail as soon as the stakes get high enough for someone to play FOMO 3D. Plenty of other bugs if you don't have redundancy. But all that, what I mean is that you will need a lot of specialized engineering. And what you really want to do is focus on your business logic, the thing that you're good at, the thing like, I want to do DeFi to help people finance whatever. I want to focus on the finance. Don't know what you're doing, supply chain, trading, whatever you're doing, you want to focus on that. The thing where you're creating value for people. You don't want to focus on distributed systems, systems programming, economic modeling, economic mechanism design, cryptography, information security, programming language use, and programming language implementation. You don't want to focus on that. And if you want, you better hire top experts in each of them, and a manager to manage all of them, and your business logic expert. That's a lot of people to get a DApp right. And so if you do a DApp today, you need all of that. And that will cost you 10 times more than hiring just a business logic guy and having us hire the other experts. By using our language, you can cut tremendously on cost by basically pooling the cost with everyone else who uses our language. So my conclusion is that at Moon, Mutual Knowledge, Moon, we are solving the hardest problems in DApps, making it safe to write them with a domain-specific language. And it's not just smart contracts, but also the client-server that comes with it. We are looking for our lead customers. If you have a killer DApp that's just too hard, please come to me with my language. We can make it doable. And of course, investors. Let's skip the business plan. The meta story is that simplicity is very important. If you want people to write DApps, you must make it very simple to write DApps. You don't want to expose your DApp developers to all these complexities that I alluded to beforehand. You can't do it. You must have simple interfaces. And yes, the implementation can be complex to a point, but the interface must be very simple. And this is possible because we need to have skills at the intersection of blockchain, economics, computing, logic, and design. All these are needed to make a good language. And the ultimate goal, of course, is to give back to users control over their digital sovereignty. We want to decentralize Internet, what people call Internet 3.0. And I think we can do it. We can do it together. Please come and join me at Moon. For more information, we have a website and white paper, et cetera, et cetera. And now I will open the floor to questions.
So please let me play the devil's prosecutor here.
Yes.
Because, so usually when I hear talks like that, I ask the following question. So the majority of these attacks resulted not from the implementation not matching the formal specification. The problem was almost always that the informal specification and the formal specification were mismatched.
Yes.
And if I look at your,
failures.
exactly. And when I looked at your source code, it looks like something out of the underhanded C context. So, where, you know, a misplaced semicolon can completely change the meaning.
Yes.
So how would you suggest to match the informal specification and the kind of code that you write in your language?
Two things. Yes, this is a very important problem. Like I wrote an article about the limits, what formal methods can and cannot do. And they can never do everything because there's always this problem of matching the reality to the code. But once again, simplicity is extremely important. With more complex systems, you still have this problem. You just have this problem like 10 times more and exponentially more complex. So you still need an audit. But auditing 22 lines of code will be 10 times easier than auditing 200 lines of code, which will be 1,000 times easier than auditing 2,000 lines of code because the complexity grows non-linearly with the complexity and the size of the code. So this does not save everything. You still need someone to audit this code. It's only 22 lines, but yes, it could be underhanded. And you probably will want to add lots of tests, lots of additional properties, etc., before you trust it. Yes, but it would be so much easier to audit the 22 lines of code than to audit the Solidity variant, and then the Tezos variant, and then the Cardano variant, and then the Bitcoin Cash variant, or whatever you have. You can check it once for this abstract 22-line thing and run it everywhere and trust it. You also need to trust the implementation, but then again, you can pool resources to check it and audit it. But that's a very important question. Thank you. Any other question? Stan, you want to say something?
Just, you know, the question which I have actually just, have you considered, like, your approach is, in a sense, revolutionary, in the sense that you're creating a new language?
Thank you.
And, yeah. But usually, it's very hard to create a new language, you know?
Yes.
There could be, you could set like a smaller goal. You could say, you know, let's take Solidity, because in reality, 99.999% of people program in Solidity. Can you take Solidity and somehow add some decorators, maybe, you know, some attributes? Can you actually, instead of trying to solve the entire problem, just somehow find a way to inject these ideas into Solidity to make it just a little bit more secure, or, you know, go the other way?
I don't think solidity can be saved. But what I do think is that you can write contracts that have like large parts that are computations done in, say, Python or Rust or whatever, what have you, and say, this computation is run in a sandbox, so I only care about the result of this computation, and I will be able to verify that the computation is correct, or at least that we agree on the result of the computation, and have a contract where the core of the interactions, the interactive part, may still be written in my language or something very close to it. Because that's the core, that's the logic you can't escape. But the rest will be written in your usual language, like you will write it in APL, Python, or whatever your financial team uses, you know, not your geeked network team. And so the financial part will be written the language of the finance guys, but it will be run in a sandbox, such that I only need to check the results. So no, not Solidity. You want the language that the financial guys use. And yes, we will be able, that's a further project. I know how to do that, but it's more work. It is already too much work. So, but yes. No more questions? Thank you very much for listening, and thank you for coming.